Good afternoon, everyone. Welcome to my podcast titled Quantum Unlocked. This podcast breaks down A level physics topics into bit sized, mind blowing chunks. I am Ayangba Omashonujon, and today we are tackling one of the most fascinating and confusing concepts in physics wave particle duality. By the end of this episode, you will understand why light can't decide if it's a wave or a particle, and how this has shaped modern tech and why Einstein called it spooky. Wavelength particle duality is a concept in quantum mechanics stating that all matter exhibit properties of both particles and waves. This means that light and other fundamental entities like electron can behave like waves or particle depending on the experimental setup. Wave-like behavior. Light, for example, exhibits wave-like behavior in phenomena like diffraction and interference, where it spread out and interfere with itself. Particle-like behavior. Light also exhibits particle-like behavior in phenomena like the photoelectric effect, where it appears to be emitted in discrete packets of energy called photon. Dual nature. This dual nature is not limited to light. Electron and other matter also exhibit wave particle duality. Classical physics limitation. The concept of wave particle duality emerged to explain phenomena that classical physics, such as the Newtonian mechanics, couldn't fully explain, particularly at the atomic and subatomic level. Examples include the double slit experiment, which demonstrate wave particle duality, where particle like electron can seem to pass through both slits at the same time, creating an interference pattern. Another example is the de Broglie hypothesis. Louis de Broglie proposed that all matter has both wave and particle properties, and that particles have wavelength and momentum. Recent advances. Recent research continues to explore and refine our understanding of wave particle duality, a fundamental concept in quantum mechanics where light and matter exhibit both wave-like and particle-like characteristics. New advancements include quantified description of waveness and particleness and the theoretical framework that relates wave-like properties, particle-like properties, and entanglements. Here is a deeper look at some recent advances. Number one, quantifying waveness and particleness. Researchers are developing methods to measure and quantify the degree to which a photon exhibits wave-like or particle-like behavior. This is done by carefully controlling the photon source and observing its interaction with experimental setup like the double slit experiment. Number two, conservation law and entanglement. Recent work has explored the concept of a wave particle entanglement, tried, suggesting that these three properties are governed by conservation laws. This research uses quantum memories and silicon integrated nanophonic chips to demonstrate that the sum of wave-like, particle-like, and entanglement parameters remain constant, a characteristic influenced by system dimensionality. Number three, double slit experiment complementarity. The double slit experiment is a cornerstone of wave particle duality, showcasing how the behavior of light and matter can be both wave-like and particle-like. Studies continue to investigate how two aspects of wave particle duality relate to each other. Application in quantum technology. The understanding of wave particle duality is crucial for developing quantum technology, such as quantum computing and quantum sensing. Recent research has explored that connection between quantum theory and information theory, potentially leading to advancement in these areas. Wave duality particle application to the real world of science. Wave particle duality, wave particle is a fundamental concept in quantum mechanics which describes how entities like light and electron can exhibit both wave-like and particle-like behavior. This duality has numerous real-world applications, particularly in advanced technology like electron microscopy, quantum sensing, and medical imaging. Here is a more detailed look at some applications. Number one, electron microscopy. Application. It is used in material science, biology, and medicine to study cell structure, analyze materials, and diagnose diseases. Number two, quantum sensors. Quantum sensors, these are devices. This device utilize quantum properties of atom ions or photons or make highly precise measurements. Application of quantum sensors. They are used in navigation systems, medical imaging techniques, and even in the detection of gravitational waves. Number three, wave particle analogy in everyday phenomena. The acoustic tweezers. These are devices which use sound waves to manipulate tiny objects like dust or cells. Photon and solar cells. Photon, which exhibit both wave and particle properties, can exert momentum, which is used in solar to propel spacecrafts. Laser cooling. Laser can be used to slow down and cool down atom, a process that also relies on the wave-particle duality of photon. Medical imaging. X-ray imaging. X-rays, which are a form of electromagnetic radiation, can be used to create images of internal structure of the body. With this, we come to an end of this podcast. Thank you.